Welcome you all. In this lecture, we are going to discuss about the influence of position of groundwater table on effective stress. In fact, this is very important discussion. Why? Because you see, in the last lecture, we had a discussion about very interesting discussion about what is the influence of groundwater table on effective stress. Influence of groundwater table on effective stress. We all realized that as the water table increases, effective stress decreases. So because of increase in pore water pressure, so there will be reduction in effective stress. Now, in this lecture, we are going to have a discussion about what is the influence of position of groundwater table. This I would like to tell you. Position of groundwater table, here you see, I will show you position means here you see in the previous case what we discussed, water table is at ground level, but in this case water table is not exactly at ground level. Now water table is somewhere between, here you see, ground level and bottom of the soil. Here you see bottom of the layer of soil. Here you see, let me tell you, here this is the position of water table. Now this one is H1, and here we can see the submerged portion is H2. So here you see the dry portion thickness is H1. Now I want to draw sigma total stress diagram. So I will start now. Here gamma D into 0, because here this is dry condition. The ground is dry. Gamma D into 0. So now I think it is okay. 0. Now when it comes to interface, that means at the bottom of this dry portion, now I can write gamma D into H1, because H1 is the thickness within the dry portion. Okay, now gamma D into H1. Now it becomes, you see, after you say, once you are entering into the second, saturated zone, in fact, it is submerged zone. So now this is going to be constant. This is going to be constant because you see gamma D into H1, which is already acting. So now it will be continued now. Now we are going to the rectangle. The reason you see why I am drawing rectangle, now gamma D into H1 is became now such as, so gamma D into H1 is constant. Now we are seeing a rectangle here. Now let us come to the submerged portion. Here you see, I can show you. This is, you see, here it is 0 because no submergence above dry condition, above submerged condition. There is no submergence, so I can write gamma sat into 0. When it comes to the bottom of the layer, one can write now, here it is gamma sat into H2. Gamma sat into H2. Let me tell you now, here you see, it is gamma sat into H2 because the portion within the saturation is, in fact, it is submergence, is H2. Now let me tell you about pore water pressure diagram. So for this, I will select another color. So let me choose a color. So now here there is no water table in this portion, H1 portion. That's why I'm writing 0, gamma W into 0. Here also gamma W into 0. Now when it comes to the submerged portion, here it is 0. But we all know this, the thickness of the submerged portion is H2. Now undoubtedly, this will be gamma W, because I'm trying to calculate pore water pressure, unit weight of water into height of water. So height of water is H2, gamma W into H2. Now let me calculate sigma dash. So for that, you see, I will choose another color once again. Here you see, sigma dash is equal to sigma minus U. Sigma minus U. Let me tell you now, 0 minus 0 is obviously 0. Now gamma D into H1 minus 0, gamma D into H1. Now it is going to be constant. Once again, I'm telling you this is a rectangle, not triangle, because what I'm trying to show you, this triangle means as the depth increases, stress is going to be increased. Whereas here you see this is now surcharge weight, because after you see once you are entering to the submerged portion, so now one can see now it is going to be constant, gamma D into H1. In fact, you see my weight of head weight, if you see a human body, so head weight is going to be increased within the portion of head. Once you reach the neck portion, the weight of the head is constant throughout the rest of the body. So that's why gamma d into H1 is constant. Now let me enter into the submerged portion now. In fact, you see here, I can write now without any hesitation. This will be gamma sat H2 minus gamma W H2. So now H2 is common, undoubtedly. I can common H2. Now what I'm getting now? Gamma sat minus gamma W, which is equal to gamma prime, which is equal to gamma prime. If you are not happy with prime, you can write submerge SUB into H2. This is the story of drawing effective stress distribution diagram from Z0 to ZH. So here we have H1 and H2. H1 is dye portion, H2 is submerged portion. In fact, once again, I'm trying to emphasize that as the water table is increasing, effective stress is decreasing. And if no water table is not there, so luckily effective stress is more here. Here you see gamma d into H1, it is same is continuing here, gamma d into H1. Whereas here you see it is gamma sat H2, now it becomes gamma dash H2. In fact, gamma dash is the least value, and you see we all know gamma dash is less than gamma sat. So one can easily understand effective stress here is going to be decreased as the water table is increasing.
Let us start this example now. So a clay stratum, here you see we have a clay stratum, 8-meter thickness, 8-meter thickness. We have a clay layer here. Its thickness is 8-meter. Its thickness is 8-meter, and very important, is located at a depth of 6 meters from ground surface. This clay layer, if you see the ground surface here, one can understand now this is located at a depth of 6 meters. 6 meters. So from ground surface, this is the clay layer. Now you see it is overlain by fine sand. Here you see we have fine sand here. This is the fine sand. Now you see here for fine sand, the water table is located at a depth of 2 meters from ground surface. We have water table, no doubt, which is located at a depth of 2 meters from ground surface. That means you see there is a water table at a depth of 2 meters from ground surface. Now the remaining portion which is submerged within the fine sand is 4 meters. So this is H1. I would like to call this H2. Now this is the clay layer, 8 meter H3. Now here you see basically when we want to calculate total stress, we need unit weights. Let us look on unit weights now. Here you see the Mach unit weight of sand is given, gamma. Let me tell you, this gamma of sand is given. Gamma is given, which is above water table, is 16 kilonewton per meter cube. And very interesting, the submerged unit weight of sand is also given, gamma prime, that is equal to 10.2 kilonewton per meter cube. Now you see what is given in addition regarding clay layer. It is very important to know about clay layer. So this is clay. They have not given unit weight directly, but GS is given, water content is given. Now very interesting, the water table is at 2 meters below the ground surface. This entire portion is in submergence. In fact, actually this portion in submergence. So now what I'm trying to tell you, this clay is basically saturated and actually submerged. So now you see this clay is saturated, degree of saturation is 100%, that I can take is equal to 1. Now how to calculate gamma saturated clay? We can easily calculate G plus E into gamma W by 1 plus E. 1 plus E. Now one can see now GS is given. How much it is for clay layer? 2.76. Void ratio is not given. but I can able to get wide ratio because I know here W is given, water content is given, GS is given, specific gravity of solids is given, degree of saturation knows, no known to us. Now let us proceed. Now SE is equal to, let me write now, SE is equal to W into GS. Now how to calculate E? WGS by SR. Now it is very important to know what is W. Here W is given, water content is given 25%, 0.25 into GS. GS is given 2.76 by 1. Now wide ratio, if you use calculator, you will get 0.69. This is regarding wide ratio. So now let us proceed answering this question now. 1 plus E. As you know, degree of saturation is 1 in case of saturated. That's why here you cannot see degree of saturation. It is 1. S is equal to WGS. From that we got wide ratio. Now 2.76 plus 0.69 by 1.69 into 9.81, which gives a value equal to 20.03 kilonewton per meter cube. Now this is undoubtedly gamma sat clay. Now I got gamma sat clay, which is equal to 20.03 kilonewton per meter cube. Now we have all gammas, gamma for sand, above water table, gamma for sand, below water table. So we know gamma saturated clay. So we are having all the data. In fact, water table is at 2 meter below ground surface. This entire portion is submerged actually. So here E is given gamma dash. So actually, gamma dash for fine sand is given. From this, we can able to calculate gamma sat for fine sand. So we know gamma prime is gamma submerged is gamma sat minus gamma W. Now I want gamma sat, so gamma prime plus gamma W. So this we can easily write now. Gamma prime is with me 10.2. So now just add 9.81. So we are getting now 20.01 kilonewton per meter cube. This is regarding fine sand. Now let us proceed how to determine total stress and pore water pressure. If you know total stress and pore water pressure, which from knowing sigma and U, total stress and pore water pressure, sigma and U, it is possible to determine effective stress. As we all know, effective stress sigma dash is equal to sigma minus U. So let us proceed now. How to answer the question now? You see, I'm going to answer the question now. Have a look on this. So these are the guidelines now. Now I'm going to draw total stress now. So let us see now. Yes, it is visible now. Yes, here you see we have one more. Actually, water table is here. Now you see this is gamma into H1. Then it is going to be constant. So now you see this I would like to write gamma 1. Otherwise you see for your understanding this is gamma 1 and this one is H1. Now gamma 1 H1, gamma 1 H1, gamma 1 H1. Now let us proceed now how to calculate total stress below the water table in sand. Now you see just extend this. Now this is gamma saturated into H2, then it is going to be constant. Now this value is gamma saturated into H2. Now let us see now what is this. What is this now? This is gamma sat clay into H3. Now this is our total stress distribution sigma. Now let us discuss about minus for water pressure. Now I will show you how to draw for water pressure distribution in this case. So all of you have a look on it. So now we are going to draw for water pressure distribution diagram. So here it is 0 because no water table is here. Water table starts from here. So what is this value now? Gamma of water into height of water is H2. Now it is going to be constant. Now it is going to be constant. Now coming to the next layer. So what is this answer now? This just now we discussed gamma W into H2. Now what is this value? Gamma W into thickness of the clay layer that we are trying to represent as H3. Now how to calculate the answer now? That is effective stress. So now we are going to calculate effective stress. Let us see now. The answer is with us now. So how to answer this now? So it is 0 at top because there is no soil above the ground surface. Gamma into H. So now 0. Now here you see there is no work for water here in this region. There is no water table. So water table starts from here. So let us proceed now. 0 minus 0 is 0. Now this will be gamma 1 into H1. And it is going to be constant. Thereafter, it acts as a surcharge, uniformly distributed load. Now you see gamma into. Now we are ready to tell this is gamma sat regarding fine sand H2 minus gamma W H2. Now H2 is common. What we are getting at the end? Gamma dash H2 regarding sand. Now what is this answer? We are ready to tell. What is this answer? Gamma dash clay into what is the thickness of the clay layer? Now you see gamma sat H3 minus gamma W H3. What it gives now? Gamma sat H3 minus gamma W H2. I'm telling you effective stress for clay layer. Now what is the common now? Gamma sat minus gamma W into, sorry, this is H3. H3 is common. Now what I'm getting now? Gamma prime H3. This is what I am writing here. Gamma prime H3. This is effective stress distribution diagram from top to bottom. Now let us complete the question now. Compute the effective stress at the middle of the clay layer. So let us discuss now the main component of the question. We need to compute the effective stress at the middle of the clay layer. Let us see now. We have answer here. Sigma, this is sigma, u, sigma dash. But the questionnaire is expecting, this is the middle of the clay layer, one can see now. So he wants effective stress at middle of the clay layer. So now you can write here, sigma dash at middle of the clay layer. Middle of the clay layer. So this will be, just see now, this is the answer now. Gamma 1 H1, this is gamma 1 H1. And one can write now gamma 1 H1 plus gamma 1 dash H2 plus gamma 2 dash, the clay layer is 2, sand is 1, easy way of representation, gamma 2 dash H3 or H3 by 2 because we want effective stress at middle of the clay layer, H3 by 2. Now let me do the calculation now. Gamma 1, I know gamma 1, it is 16. I know H1, 2 meter plus gamma 1 dash. What is gamma 1 dash here? It is given actually in question 10.2. 10.2 into what is the portion of the sand below the water table? Here one can see undoubtedly the thickness of the sand is 6 meter. A portion of the sand below the water table is 6 minus 2, which is 4 meter. 4 meter plus gamma 2 dash. What is gamma 2 dash? Here you see it is very easy to tell. Gamma 2 dash, just now I calculated for clay layer. This is clay's second portion, second layer. Now you see sigma dash clay, gamma sat H3 minus gamma W H3, gamma prime. Actually, how to calculate gamma prime now for clay? Gamma prime clay is equal to gamma sat clay minus gamma W. Gamma sat, we have done an exercise about how to find gamma sat for clay by using fundamental relationship. Gamma sat is equal to G plus E gamma W by 1 plus E, where degree of saturation is 1 because I am writing saturation. Now one can see now here I got gamma sat clay 20.03, 20.03 minus 9.81. That gives a value 10.22 kilonewton per meter cube. Now let me finish the question. Now we have gamma 2 dash 10.03 into H3 by 2. H3 here, as I told you, it is 8 meter, 8 by 2. Now we are getting an answer. Let me show you the answer now. Sigma dash at the middle of the clay layer is equal to gamma 1 H1 16 into 2. So plus 10.2 into 4 plus 10.03 into 8 by 2. 8 by 2, which gives an answer 113.68 kilonewton per kilopascal. Kilopascal. This is the way we use it to calculate effective stress in case of layered soils in which water table is present. So first we are concentrating on total stress, then pore water pressure, and finally we are determining effective stress. One can see here sigma u, no water table, u is 0. If water table is there, you gamma of water into height of water. Here you see height of water is h2. When it comes to the second layer, it is h2 plus h3. That's why I'm writing, you see gamma w. If you common gamma w, it gives gamma w into h2 plus h3. But whereas here you see we have only h2 only in sand layer. When it comes to second layer, both influence of above layer is also there summing up. This is what happening here. You see gamma 1 h1 plus gamma sat h2 plus gamma sat into h3. That means you see here once you see once you're coming down, the influence of the upper layer is also acting on lower layer. So it will be summed up. Here it is gamma 1 h1. Here it is gamma 1 h1 plus gamma sat h2. Once it is reached the third layer, here you see gamma 1 h1 plus gamma sat h2 plus gamma sat clay into h3.